Okay, so this is problem 2.4 out of Griffith's Electrodynamics. And in this case, we have a square loop that carries, I should say, uniform line charge lambda. It's a square of side A. And we want to find the electric field a distance z above it. So, if you could imagine at some point like this, if you can imagine a triangle kind of like this, where this is your height z, since it's right above it in the center. This is a over 2, since the whole length is a, and this is script r. And we can start with, just imagine doing this for one of these four sides, and we'll call this angle theta. Okay, now our electric field is going to be, the lambda's constant, so I'm going to pull that out, 1 over 4 pi epsilon naught lambda, the integral of 1 over script r hat d tau. Okay, so let's get a few things together first. First, script r, just from this diagram, I think it's pretty easy to see, is a squared over 4 plus z squared square root. And obviously, since we want script r squared, that just gets rid of the square root. The other important thing to know is the direction. And this follows a reoccurring theme with the last few videos. Hopefully you can see that any contribution, let's just take a random line segment here, any contribution in the your x component, for example, or your y component, however you have your coordinate system arranged, will be canceled out with this part. So these two will have, depending on how you set it up, I guess, a z component, but also a x component. And the x components are going to be equal and opposite. Meanwhile, over here, you'll have a similar feature, except they'll cancel out in the y, for example. So, in other words, you're only going to be left with a z component for your electric field. So, it'll be in the z hat direction. Okay. So then, if we want to find the electric field from one of the sides, it'll be lambda over 4 pi epsilon naught. We'll integrate over the entire line, and we'll have 1 over a squared over 4 plus z squared. Now remember, we just want the z component of this. So that'll just be your sine theta part, right? Since that's opposite of our angle. So we'll multiply this by sine of theta. And of course, we're going to integrate over dx. So we'll just let, for example, this be the x, maybe this be the y. And hopefully that makes sense how everything cancels if you see it like this. But you could have set your angle differently. It doesn't really matter as long as you're consistent. Hopefully this all makes sense. Sine of theta is going to be the opposite of the angle. So the opposite is obviously z over the hypotenuse, right? Which is going to be script r. So that'll be z divided by a squared over 4 plus z squared, and instead of the square root I'll write it as 1/2. And we can plug this in for sine of theta, and you'll notice we'll have a lot of constants there. Everything in there is actually a constant. This is to the first power, so when we multiply those, what we have in the denominator, we can combine those. So we'll have lambda over 4 pi epsilon naught, and the integral from, let's just factor this stuff out as well, times z over a squared over 4 over z squared. This will be to the 3/2 for our exponent. And then when we integrate just dx, we're going to get x evaluated from 0 to a. So essentially we're just going to get a here. Now this, remember, is just for one of the lines. However, by symmetry, if you can imagine, it's going to be just all 4 of those added. So everything's going to be the exact same because of the symmetry. So all we really need to do is take this answer and multiply it by 4 if you want to find the total E field. It's just 4 times the E field that one of the lines produces. So 4 lambda a z, and this is in the z hat direction, all over 4 pi epsilon naught times a squared over 4 plus z squared to the 3/2, and again this is in the z hat direction. So hopefully that makes sense. If it did, please like and subscribe, and I'll post more solutions from this textbook.